Okay, so last time we defined the Kolmogorov complexity. And we said that we fix some programming language. We fix a programming language. And then we say that k of x is the bit length of the shortest program that outputs x and holds. So this is on an empty input. The program needs to output x. In other words, it's kind of the length of a description of x. I want to describe the string x, and I want to define the shortest description of x. And if you remember that we had in the first lecture, we talked about the Barry paradox. And the Barry paradox said that if I look at the set of all strings, of all numbers that can be defined by at most 200 English characters, we got a paradox because we didn't fix the language in which we were describing those numbers. You remember I asked, is it a finite set or an infinite set? So in order to avoid this paradox, we fix the programming language, and instead of just saying describe the string x in English, we say write a program that will output x. But it's the same thing. You just describe x in some well-defined way. So that's the Kolmogorov complexity of a string. And the thing to notice was that most of the strings that we come across are always short. What I mean by short? So by short, let us just start with the following. So in some sense, most binary strings have high Kolmogorov complexity. And what do I mean by high? So what I mean is that, or minus something, right? So for every, or let's fix it to 2. But we will see that this is for every. So if I look at the set of all x's such that k of x is at most the length of x minus 2, and so let me say, let us fix the length. So such that the set of all x such that k of x is at most x minus 2, but let's give it a name. So, and the length of x is n. So this will be the nth set, and I'll divide it by the set of all strings such that the length of the string is n. So I'm looking at all the strings of some fixed size n, and I want to ask which fraction of them have Kolmogorov complexity which is less than the string. Now note that I can always, this is something that should be obvious, that for every x, k of x is at most x. Why is that true?
Hard code x into the program, so we can write them.
Yeah. I mean, you can give me the assignments at the end. Yeah. You don't have to crawl under the tables. So I'm saying for all x's, k of x is at most the length of x, because I can always write a program that will say print 0, 1, 0, 0, 1, 0, 0, 1, and so on. So the length of the program will be x plus the command print. So it will be some constant. So now I'm saying, okay, so this is a complex string because this is as complex as it gets. So now I'm asking how many strings are not so complex. The length is less than, just by 2 bits, less than the trivial description. I can describe them a little bit more compactly than telling you bit by bit what the string is. And what I'm saying is that this number is going to be small. Why? The reason is that I can say, we have seats there. You can grab a cookie as you pass. Hop, hop, hop. Okay, so what I'm saying is the following. So we know what is in the bottom line. These are binary strings. So what is this number, the length of all strings of length n? What do I know about how many strings are of length n? 2 to the n. So this is 2 to the n. But what do I know about the nominator? About the nominator, I know that this is less or equal than the size of all p, such that p is a program of length at most n minus 2, right? Because every string here has a program that computes it. And since its Kolmogorov complexity is less or equal like minus 2, then the program will be of that length. That's what the Kolmogorov complexity means. But this is the bit length of the program. So how many programs do I have of lengths like this? How many? I mean, a program is just a string, a binary string. So this is at most 2 to the n minus 2, and over 2 to the n, which is a quarter. So the strings that have, you see, the strings that have Kolmogorov complexity, which is only a tiny bit less than telling you explicitly bit by bit by bit, they're already a minority, just a quarter. And if I said here, instead of have length x minus 2, if I have here have length at most x minus 10, then what I will have here is n minus 10 divided by 2 to the n, and here I'll have 2 to the 10. So we know that most of the strings are almost as complex as you can get. Yes?
Because the length is at most n minus 2, shouldn't the numerator be 2 to the n minus 1? Because it's like 1 plus 2 plus 4. Because you can have programs of smaller lengths as well. Like the number of programs of length.
Are you talking about the nominator or the denominator?
Denominator, yeah. Because
the denominator?
the numerator, the top.
The top.
Yeah, because the length at most.
Oh, at most, right, right. So let's make it right. So let's make this 3. Okay, yeah. Because it's the sum of all shorter lengths. It's not just strings of length n minus 2. They're also shorter strings, and they can contribute a little bit. Okay. But basically, I mean, the idea is that by just counting programs, we know that there aren't enough programs to produce many small complexity strings, so most strings have long complexity. Okay? But, of course, you cannot show me any such string. I mean, if you try to describe a string, and I want you to give me kind of a recipe, that for every n will output a string of length n which is complex. And complex means its complexity is above x minus 3. Right? You cannot give me a program that will do it. Why not? Yeah.
Because you could just have the program as your program, and for large enough n, you could say the program and then what this program outputs.
Right. At least there's almost perfectly correct answer, except that you also need to give n as an input. If I had a program that for any n, for every n, will output a string of complexity greater than n minus 3, then the string that the program outputs has the description, which is the description of the program, which is constant, plus the input n, which is log n, which is smaller than n minus 3. So I got a contradiction. So I cannot have a program, I cannot have a recipe that will generate complex strings, although most strings are complex, which is kind of a very strange phenomena, but we see such phenomena in mathematics. For example, we know that most of the real numbers are not only that they are not rational, they are not even algebraic. You know what an algebraic number? Algebraic number is if it's a solution of a polynomial equation with integer coefficients. So like square root of 2 is irrational, but it's an algebraic number because it's the solution of the equation x squared equals 2, which is a polynomial with integer coefficients. But pi is non-algebraic. I cannot write a polynomial such that pi will be its solution. And we know of another irrational number which is not algebraic, which is e. And that's about it. But we know that if you just randomly pick a real number in the 0-1 interval, the probability that you will see a number which is non-algebraic is, you know how much? 1. So they're the vast majority, but we cannot point to more than 2 of them. Maybe pi to the e, e to the pi. Okay, we get to 4. So it's a similar phenomena here, but here it's kind of very blatant. I mean, just in your face. You cannot give me a recipe that will produce numbers which belong to the strings that belong to the majority. Because the minute you give me the recipe, whatever your recipe outputs is minority. And, okay, so this is one interesting aspect of the Kolmogorov complexity. So if I just randomly draw a string by tossing an unbiased coin time after time after time, then I know that with probability 3/4, I will generate a string that will have a complexity more than x minus 3. With high probability, 3/4, if I just toss a coin, I'll get a complex string. But as we discussed last time, I cannot give you a recipe for this. Because my recipe, if I will be just toss the coin n times, the number that you will get will be different than the string that you will get will be different than the string that I got. So I didn't define it. Yes?
But the point is, once you generate a string that has a complexity of n, didn't you just make a program that generates full complexity strings?
What do you mean?
Okay, let's say there is a 3/4 chance that by flipping a coin you create a
Right.
string of complexity n.
Right.
Then do we have an algorithm to check if it's a
Okay, so that's the next interesting question. Do we have an algorithm that I will give you a string and you can check whether it's complex or not? Right? So let's show that we don't have any such algorithm. So this is a fun algorithm. What? What do you say?
Can you just iterate over every single program small enough?
Let's just see what happens. So this is a kind of the first, you see we're not switching from logic to algorithms or complexity, but we will get back to the logic. Okay, so here is a theorem. There exists no program. There exists no program that checks the Kolmogorov complexity of strings. So let me be more precise. Namely, my program, a program that takes a pair x, k as input, and it holds at some point, and outputs yes if and only if the complexity of x is exactly this k. So I want a program that I will give you a string, and I will give you a guess what is the complexity of the string, and the program will compute, and tell me whether it was correct or not. That's what you were kind of asking for, right? Whoever it was. So no such program exists. And we will see that, I mean, this is kind of it's almost like playing with paradoxes, but this leads to maybe the most important theorem in mathematics. You'll see. I'm not joking, I mean. Okay, so why can't there be such a program? Do you have an answer here?
Because if you try and do what Mark suggested and enumerate over all programs and try them, you'll have to run the program, and if the program keeps running for a long time, you don't know whether it's going to output the answer eventually or whether you can stop it and move on to the next one. You can't tell if something's an infinite loop that will never halt and your algorithm will never finish.
Okay,
or it'll stop.
so I have two comments about what you're saying. Three comments. First, it's a good intuition. Secondly, all you show me is that the idea that Mark suggested doesn't work, but maybe there's a better idea. Thirdly, we didn't prove that we cannot decide whether a program will halt or not.
Except on assignment.
What?
Isn't that on assignment 4?
And we will prove it now, and then based on this, we'll do the assignment. Yeah.
Well, my guess was because we already said that there will be no program that can generate a complex string.
Okay.
So if we can have a program that check if a string is complex, then by tossing a coin and check if the string generated by the coin is complex, we already have a program that generates complex strings.
Kind of. That's a better intuition, right? So let's do a formal proof. So here is a proof. So assume by way of contradiction. So this is a proof which is not by generalized induction. Right. Assume by that P is such a program. And now pick some number k that is such that k is greater than log k plus, or if you want, 10 log k plus 10 times the length of p. See, because, you know, as k grows, the gap between k and log k becomes bigger and bigger and bigger. So I can always pick, no matter what the program length is, I can pick such a k. So I picked a k big enough. You gave me your program that allegedly does the job, and I picked k big enough. And now I will show you, it is very similar to the Berry paradox that you saw in the beginning. I will show you how to generate the first string that has complexity more than k. Okay, so here is a program. So now here is a program, let's call it Q, that generates, that finds, or generates the first a binary string y such that k of y is greater than k. This is the k that I picked here. Okay, so how will the program y go? I will go over all strings. So enumerate. So here is the program Q. And it goes like this. Go over all strings. So for, how shall we go it? How shall I write a loop that just goes over all strings in lexicographic order? Okay, so for x equals the empty string 0, 0, 0, 0, 1, and so on. I'm going over all strings in lexicographic order. It's very easy to write it. I'm just too lazy to do it. Okay? For x, apply P to check if the Kolmogorov complexity of x equals k. Because we assume that P knows how to check it. Okay? And output the first one on which you get the answer yes. So the first string such that say the complexity equals k. Doesn't matter. Okay, output the first x on which P of xk equals yes. Let's call it y. So call the output y. Okay? What is the Kolmogorov complexity of y? I mean, what does the program P tells me? The program P tells me it's Kolmogorov complexity of k. Is k. Should be k since P says so. Right? The program P checks, and it's the first one on which it says yes. But on the other hand, the Kolmogorov complexity is much less than k, because I can write all of Q. What is the complexity of Q? The program Q generates y. Q generates y. What is the length of the program Q? Let us check what is the length of the program Q. The program Q, so this is a constant. This is all constant. The only thing that's not a constant is I had to write here k. So the length of the program Q is, I needed to specify k, and then I wrote this program. So it's kind of the length of Q is this program called P. So I needed to have the length of P, plus I needed to write the number k, which is log k, plus some constant, which is the number of bits to write this program. The number of bits to write for a binary strings go lexicographic order, invoke P, if yes, do so, if no, do so. It could be not a constant, let's call it 20. I can do it in 20 bits. Right? So we get that the Kolmogorov complexity, therefore, but Q outputs y. So therefore, the Kolmogorov complexity of y is at most P plus log k plus 20. But on the other hand, the Kolmogorov complexity of y is k, and k is bigger than all of that. So we got a contradiction. Yeah. On one hand, I got the Kolmogorov complexity of y is k. K of y should be k. On the other hand, we saw that k of y is less than this. So k of y is k. And k, I know already that I picked it to be bigger than 10 log k plus 10 times p or plus p. And on the other hand, I get that it's less or equal than p plus log k plus 20. But that's a contradiction. Yeah. Yes.
What if txk never says yes?
What?
What if txk never says yes?
Oh, there is, because we know that most of the strings, if you get to length k, most of the strings of length k have complexity k. That's what we showed before. So we don't even know how long we should run. Once we get to strings of length k, most of them have complexity k. Once we get to length k plus 3, most of them has complexity k. So we will find many of those. Yes?
How do you know your programming language has, like, so you wrote Q in the programming language, right?
Yeah, right. So I want kind of universal programming language. I mean, we fix. Let's our programming language. Which is your favorite? C++, Java. What do you want? What?
Really simple.
Doesn't matter. Any program can implement this kind of thing. If you have a program P in your language, then you can implement for strings in increasing binary order. K is a fixed number. K is part of your input. Check if P of kx equals yes. If not, move to the next string. You can write it in any programming language. And that's a good point. I mean, we assume kind of implicitly that we're only using universal programming languages. Universal programming language is a programming language that can program anything which is programmable. But any language that you see is universal. That's something we already know, right? It doesn't matter which programming language you use, you will always be able to, if you can program something in one language, you can do it in the other. Because the compiler does these translations. Okay? So we proved that we cannot decide what is the Kolmogorov complexity of a string. And this is very similar to the Berry paradox we saw at the beginning of the course. You remember we talked there about are there infinitely many numbers that can be described by an English sentence with at most 200 characters. And we said, sure. I mean, it must be a finite set because there are only so many English sentences with 200 characters. But if it's a finite set, then there is the first number that cannot be described in English with 200 characters, and I just described it with less than 200 characters. But there, the catch, the paradox, stemmed from the fact that English is not a well-defined language. We said we need logic, we need something more precise. And here I'm making it precise by saying I fixed my programming language. It's all done in C++. And we get the same type of, I mean, it's not a paradox. It just says there's no program that can check Kolmogorov complexity. Okay? So we got this kind of interesting result, but this interesting result it looks like a game, but this game is really revolutionary. So it leads to the two most important results of the 20th century in mathematics. I'm not exaggerating. Just from this little trick. So first of them is the halting problem. So what is the halting problem? The two theorems I can tell you already as a spoiler. The two biggest results of mathematics of the 20th century are that the halting problem is not decidable and Godel's incompleteness theorem. And we are going to prove both of them in the next 20 minutes. Yeah, it's really funny because, anyway, let's not fast forward, let's keep our pace. So, what is the halting problem? The halting problem sometimes is called pH, and so on. Halting problem, HP. Okay, HP. The halting problem is as follows. I give you a program, and I give you an input, and I ask you, will the program halt if it ran on that input? So you get as input, you take as input, your input is a program P and potential, an input, or a string X, and what you want to output is will P halt when run on input X. So you just want to get yes or no to this. Now this is an important problem because if I write a program and I want to make sure that I wrote a program that makes sense, one of the things I want to check is that my program is not just getting into a loop. It would be very nice if I could check whether my programs get into an infinite loop. If it tells me, yes, you're going to get into an infinite loop, then I will say, okay, let's fix the program. Yeah?
Kind of going backwards, but I guess somewhat related to this. In the previous thing, isn't K actually a program? Because the output of the Kolmogorov complexity is a program, right?
No, no.
Oh, no, right. It's the size of a program.
It's the size of a program. It's a number. It's a number. It's the bit length of the shortest program that outputs a string. So it's just a number, a natural number. Okay? Okay. So the halting problem is a very important problem. It's kind of a basic problem in program verification. If you give me a program, I want to verify it. I want to know that I have an input before I start running it I want to know whether it's going to halt or not. Because otherwise, I run it on my input and it doesn't halt, and I don't know whether it's because I wasn't patient enough or because it's hopeless, and on this input it will run forever. So it would have been very nice to have such a program. And the result is that no such program exists. So I don't even know whose result is this. What? Who? Oh, you think it's Turing, all back to Turing? Okay. So here is a theorem. So we are going to really reprove results by great minds today. This is Turing, and the next one is Godel. Okay. So no such program exists. In other words, there is no program that on any such input Px will halt and tell me whether the program P halts on X or not. And that's a major observation in computers, in computer science, because it tells you there are tasks which are well-defined, mathematical tasks. I ask you a very legitimate question, will this program halt or not? But computers cannot carry out those tasks. So here is the proof. And the proof now goes back to the idea that you suggested before. You suggested? So here is the proof. Assume by way of contradiction that such a program, let's call it H because it solves the halting problem, exists. So our program now, it takes as input a pair X and P and tell you whether the program P will halt on X or not. And On every such pair, it will halt and tell you the answer. Now I will show you that using such an H, you will be able to solve the Kolmogorov problem that we know that doesn't have a solution. So now we claim if we have such an H, we can compute the Kolmogorov complexity problem. And that's a contradiction, because we just showed that you cannot. So this little trick goes a long way. It shows us it solves the halting problem, proves the halting problem theorem. And the proof is very simple. What will be the proof? I give you, here is how you do it. So here is the proof of the claim. So you get an input. On input x and k. You want to check whether the Kolmogorov complexity of x is k. Right? You just go, so again, it's kind of go over all programs in lexicographic order. So you start with the empty program, and every string just check if it's a program or not. If it's a program, on any program that you come along, so how shall we call it? Now we've already exhausted our P's and our F's. Yeah, it's not a good name for a program. Okay, let's call it capital J. But you go over all program, apply H to check if J holds on the empty string as input. Okay? If it does, if H of J empty string is no, just move on to the next program. If it does, if H of J on the empty string is yes, you know it's going to hold. Just run it till it holds. And now check. Did it output X? I want to check whether the Kolmogorov complexity of X was K. So I'll go over all programs and find the shortest one that output X. This program that I gave you now finds the shortest program that output X, because it goes over all programs in order of their lengths and check if they output X or not. The only thing that could go wrong with such a thing is what you suggested. You know, we don't know whether it will. I'm trying to run a program to see if it will output X. It's run, it's run, and run. I don't know. Is it going to output X one day, or is it just going to loop forever? But now I don't have to worry. H will tell me. Once H tells me the answer, I can carry out what you suggested as what you said, you call it the mark program? Yeah. So your suggestion of the mark program will work once I have a subroutine that can check halting. But since we know that we cannot check Kolmogorov complexity, we prove that halting cannot be done. See, and we prove that halting cannot be done without having to, I will refer to, I don't know if you know it. Have you seen the halting problem before in a different course? Have you seen the What? Have you seen the Dr. Seuss? There is a poem, the Dr. Seuss poem that describes the proof to the halting problem. So I will upload it. It's real fun. It's really nice. It explains the proof very nicely. Not my proof. This is my proof. But any proof that you see in the course kind of involves diagonalization. You create this program that says, I hold on myself if and only if I don't hold on my cousin or something like that. Here we don't need anything like that. Everything runs very smoothly, no diagonalization. Okay, we proved the halting problem. Now, before we move on to prove Godel's theorem, some comments on this. What we proved here is that there is no program that checks whether on a given input, a given program you halt or not. But what follows from this is that tons and tons of other tasks cannot be carried out. So as a consequence, many other tasks cannot be done by programs. So for example, here is example 1, input a program P and ask, does P halt on the empty string? Does it halt on the empty string? We already showed, because this is all we needed here. But we can ask all kinds of things. We can ask input P, does P halt on any string at all? Which looks like a different task, right? And the way to, and there are so many, let me just prove to you this one, and you'll see that this is kind of a funny, stupid game. Once you get used to it, you can do everything like that. And in fact, there is a theorem that basically says you can do nothing. Or more precisely, it says any questions about programs and halting cannot be decided. And there's some notion of every question cannot be decided. But let me just show you how easy it is. You see, on the surface of it, this one we just showed. All we needed to show to get the contradiction with the Kolmogorov complexity is a program that checks whether you halt on the empty string. But of course, if you can't even check that you halt on the empty string, you cannot do the task of I give you a string and I give you a program and will you halt on this string? Because this is a specific case. But what about asking you, is there any string on which you will halt? I will show you that trivially this also cannot be done. Why can't it be done? Because, so here is proof of 2. So assume, by way of contradiction, that such that a program exists. And the trick is that we will use it as a subroutine. We will use it as a subroutine to solve 1 that we already know cannot be solved. I mean, it's the same kind of construction that we had here. We said assume that you have a program that solves a halting problem. We'll use it as a subroutine to solve Kolmogorov complexity. What will we do? So let me draw a diagram. So the idea here is like this. I want something that I will input a program here. You will give me a program P. And here as the output, you will say yes if, you'll say yes, if P holds on some input, and it will say no if P loops on every input, right? And we want to show that no such program exists. And here I will use as a subroutine. Oh, sorry. The other way around. Right. The other way around. Right. So I'll use a subroutine. This is my P. Okay, so I don't have to rewrite it. So assume that I have such a P. I will use it in a subroutine in a bigger program. Just don't have enough space. Okay, I'll use it as a subroutine in a different program. That this other program will get a program, call it Q, and output does Q halt on the empty string. Since we know that no such big program exists, we cannot have this subroutine as a black box. Okay, so how do we do it? Given Q, I will write a new program P. So given Q, my P will be as follows. So what will be my P? My P will be P on every input X, ignores the input, ignores X, and runs Q on the empty string. So now, if I know if P holds on some input, I know that Q will hold on the empty string. You see? I just cheated. As I assume that I can check whether you hold on, right, on some input. So I wanted to check whether Q will hold on the empty string. I gave you a P. And you claim that you can check whether P holds on some input. Here is my P. It holds on some input if and only if Q halted on the empty string. Because on every input, what this P does is just ignores the input and runs Q on the empty string. So if there's any input on which P holds, if the answer here is yes, I know that Q holds on the empty string. Okay, so this is a bit mind-boggling, but it's really simple once you digest it. And this is called reductions. So we use reductions to show that once we know that one thing is undecidable, cannot be decided, we can show many things are undecidable. And I think you have a couple of more of these in the assignment, or one more of these, or what? I mean, I will not go more with reductions. I really would like to have it in the exam, but so I'll give you more practice examples of this. And because you see, we now did a diversion to computer science, to programs, talking about programs. It doesn't look like logic. And I want to steer it back to logic. I don't want to spend too much time on this. I want you to get the basic idea. We proved what we needed. But I want to steer it back to logic. And with logic, we have a very important task, and that's the Godel incompleteness theorem. So let's talk about that a little bit. And we'll see how with this we can prove the Godel incompleteness theorem. So what is the Godel incompleteness theorem? It's so the story starts with the beginning of the 20th century. So in the beginning of the 20th century, there was a lot of optimism in science. I mean, we saw huge breakthrough in science. Do you know, like, examples of great things at the beginning of, yeah, what is?
So there's modern physics with things like quantum mechanics or relativity.
Right, right. Einstein, relativity, yeah. What? Principia Mathematica. Yeah, so Russell, it's also, but, and also, I mean, completely different area, there was Freud that started modern psychology. He was also living in the same time, beginning of the 20th century. I mean, everything was booming, everything was being discovered, wonderful. So the biggest mathematician of that era was Hilbert. So Hilbert was the greatest mathematician of that time, and Hilbert had a plan for mathematics. He wanted to say, like, he had a kind of a big vision. He already was acknowledged as the greatest mathematician of his time, and he knew that he was. So he said, okay, let's do something more than just solve problems. I will show the way for future mathematicians. And so there was this Hilbert's program. And the Hilbert's program, the idea was, here is the most important plan for mathematics. He also had a list of the most important problems. I don't know if you heard about it. The Hilbert's tense problem, he had a list of open problems. Most of them are solved by now. But the Hilbert program will say, you know, we're doing mathematics all the time, but we have an intuitive notion of what is a proof and what is not a proof. I mean, it's lucky that no mathematicians kind of disagree on what is a proof and what is not a proof, but it seems like just a matter of luck. We really need precise notion of what is a mathematical proof. So we should formalize the notion of a valid mathematical proof. And by the way, I mean, at that time it was relevant also, I mean, if those of you that came to the special lecture on like a few Wednesdays ago, when Cantor came up with his proof that there are different infinities which are not equivalent to one another, so people were kind of questioning his proof, saying, is it a valid proof? Well, this is what he's saying doesn't make sense. So Cantor, when these different infinities, was also the same time, the beginning of the 20th century. And this was a real question. So that was his program. Let's have a formal basis for mathematics. We really need it. And what do we want such a notion of a valid mathematical proof to satisfy? So it should satisfy the following three requirements. And we've seen those requirements before. So what are the three requirements? First of all, we want soundness. But what does it mean, soundness? We have to be more precise about it. So we want soundness, but we talk about a proof system for mathematics. So let's be modest and just say we want a proof system for statements about number theory. Number theory is the kind of the bread and butter of mathematics, the theory of natural numbers. Prime numbers, complex numbers, not complex, composite numbers, prime numbers, solving least common denominator and so on. Okay, so soundness, what we mean by this that if my system for every, and let's be very precise, first order, but it doesn't really matter. Okay, first order statement about natural numbers say phi, if my system can prove phi, then phi is a correct statement. So phi could be there exist infinitely many primes, and so on. Okay, so soundness is a very natural requirement. But and we have soundness is not so difficult to come by. I mean, I can give you a proof system with no proofs, so it is sound. Whatever it proves is correct, vacuously, because it doesn't prove anything. So that's not a real challenge yet. The next challenge makes it really more interesting is completeness. So what do I mean by completeness? And this is that every true first order statement phi about natural numbers is provable. So we want to kind of to found mathematics on solid grounds. So we want that we have a notion of what is a mathematical proof. Mathematical proofs guarantees correctness, and every correct statement is provable. Now you can say, oh, that's a bit too much to ask for, right? But we have such a system. What is the system that satisfies both soundness and completeness? What? Propositional logic doesn't tell you everything you want to know about natural numbers. Yes?
Enumerations of all the numbers. Wait, no. An infinite proof system where the proofs were infinite in length and contain every possible natural number.
I don't have to go to infinite. I will just take as my proof system, my axiom will be all the true statements about the natural numbers. I will have no deduction rules. My axiom will be the set of all true statements. So clearly, if I prove something, it's true because it's an axiom and the axioms are true. And clearly, every true statement has a proof, which is an axiom. Yes?
So you also need a formal proof for your axioms?
What do you mean? No. This is the usual game that we play. You have a set of axioms. You have deduction rule. You have a notion of a proof. Right? So we want to avoid this. What's wrong with that? What is missing in... I will answer Hilbert and tell him, here is a solution to your problem. Me, Shai, I can solve Hilbert's problem. What's wrong with this? Yes?
It needs to be verifiable.
Right, it needs to be verifiable. So 3, it needs to be verifiable. So there should be, so let's call it verifiability. So there should be a clear formal method to check if a given a string of symbols is a valid proof. So I give you a string of symbols, I give you a statement phi, you should be able to check whether this is a proof or not. Yes?
Isn't formal method a bit ambiguous? Wouldn't it be better-
Right, so formal method is a bit ambiguous, but so let's replace formal method by algorithm. Algorithm in C++.
That halts maybe?
What?
That halts maybe? You
Yeah,
want your proofs to-
yeah. So checkable means on every alleged proof, it will halt and tell you whether it was a valid proof or not. Okay. But of course, when Hilbert stated it, he did not talk about C++. It was, the old days, they were using Fortran. Okay, so that was kind of his big program for mathematics. It looks like a real challenge. Now, let me ask you one question. We talked about first-order logic. We talked about soundness, we talked about completeness. We have a method of checking what is true and what is not. So isn't the axioms of first-order logic already an answer to Hilbert? Yes.
So there are statements about natural numbers that first-order logic cannot state.
But we claimed that it's sound and complete. What I'm asking is, why is the soundness and completeness not of first-order logic not solve the problem? What? Okay, so it's really kind of a confusing question because we use the same terms. But when we prove soundness and completeness in first-order logic, it was the axioms. So just note the axioms, the proof system of first-order logic that we saw is indeed verifiable and sound and complete, but we have a different notion here. With respect to the set of all phi, such that phi is a logical truth. So note the difference. Here, we want soundness and completeness with respect to all statements which are a logical truth. Here, I want soundness and completeness with respect to all statements that hold in the natural numbers. And this is a different set. So, which of them is bigger? Yeah, natural numbers is bigger. Because if I have here, if this is the set of all phi's, and these are phi's true in the natural numbers. These are logical, valid phi's. They are much smaller. Because if something is logical valid, it holds in every model, in every structure. But there are many formulas that hold for the natural numbers and are not a logical truth. Can you give me an example of such a guy? Something that is true for the natural numbers, but it's not a logical truth. Yes?
For any number in natural numbers, there is a finite predecessor of it.
That's, you're getting way too difficult. I will just say for every x, there exists a y such that Rxy, where say R is the ordering. For every number, there is a bigger number. It's definitely true in the natural numbers. but it's not a logical statement. It's not a logical truth. I can come up with a structure in which it's not true that for every x there is a y such that rxy. Right? R here stands for the ordering in natural numbers. So that's not a logical truth. It's very easy to come up with a structure in which it's not true. Right? Just take the natural numbers and interpret R as less than rather than bigger than. And suddenly it's not true. So logical truth is a small subset. So sure, if I have something that has to be able to prove every statement true about natural numbers, it should be able to prove every logical truth. I can take the proof system, this proof system, as a subset of my axioms. But I need more. I want to prove what is true in the natural numbers. I want to do mathematics, not just to do logic. Okay, we have soundness and completeness for logic. But for mathematics, I want to talk about natural numbers, not to talk about numbers. Natural numbers is a start. Okay. So these were the Hilbert's program. This is a very natural thing to ask for. And Hilbert was hoping that mathematicians will be able to come up with such a system. Now, we do have axioms for natural numbers. We have the axioms for logic, and we can add to them axioms for natural numbers, things like saying the addition is a billion, commutative. And we can say 0 is the least number. And we can say, as you see in the assignment, the principle of induction. Every formula that holds for 0, and if it holds for n, it holds for n plus 1, holds for all numbers. So there actually is a proof system that is commonly used for proofs for the natural numbers. And this is called Peano arithmetic. And Peano arithmetic has axioms like saying, this is transitive if x is less than y and y is less than that, and x less than that. And it says this is commutative. And times is commutative. And the induction principle. And in general, there are about 10 such axioms. And they usually suffice for anything that we want to prove about natural numbers. So there are some more. But they just describe the basic properties of the natural numbers. In the language, we have to fix the language. Let's say our language has R, which is a binary relation for less than. We have A and B for 0 and 1. And we have F and G for plus and times. Some basic components of arithmetic. So we have such a language, we can write those properties, and that's called Peano arithmetic. And that was kind of a common framework. It's still a common framework for doing proofs about natural numbers, or proving things about natural numbers. Okay, so there was even a suspicion. You say, the Peano arithmetic, which of the three properties does it satisfy? Yes?
Soundness and verifiability.
Right, it's sound and it's verifiable. So there was even maybe a hope that it can be complete. And now comes Godel and says it's not complete. And he even says something very amazingly strong. He says, So Godel came like 20-something years later and says, no, so this is Godel, and it says no such system exists or can exist. So in particular, for every proof system that is verifiable for numbers, number theory, that is verifiable there is a statement about numbers phi such that you cannot prove phi and you cannot prove not phi. Because, you see, if we are not complete, we are sound and not complete, then we have a statement phi which is true, but I cannot prove it. Right? Everything that I can prove is true, but it's not complete. So there's something which is true and I cannot prove. So this is my phi that I cannot prove. Why can't I prove not phi? Because of soundness. Phi is true, so I cannot prove that it's not true because I'm sound. Right? So failing completeness while having soundness means that I will have a statement that I cannot prove the statement, I cannot prove its negation. And here the number theory is only the tip of the iceberg. I mean, there's all of mathematics. Number theory is only the simplest object that mathematics is looking at. So the same holds for any complex enough mathematical object. So the natural numbers are just the simplest one, but we can have the same statement about real numbers, about complex numbers, about algebra, about any rich enough mathematical. No matter what axiom system you come up with, there are going to be statements that you cannot prove and cannot disprove. And now, this is a big revolution in mathematics because, I mean, just think of it. Until now, and I think everybody who is not a real mathematician kind of feels that if you have an open question, we have this question, here is an open question we all know about. Does P equals NP? Right? So, we believe that, sure, we don't know the answer. But if we'll work hard enough, we'll be smart enough, we'll find an answer one way or the other. But what Godel tells us, it could be that there is no proof that P equals NP, and there is no proof that P is not equal NP. So it's a big revolution in mathematics. And before Godel, people were thinking, okay, there are two types of statement in mathematics. Things that we can prove and things that we can refute. Oh, there are things that we haven't done it yet. We didn't find the proof yet. But if we work hard enough, we'll find it. But Godel says, no, there's a third type. Those that we cannot prove and we cannot refute no matter what we try. And you can say, who? That's, I will cheat Godel. I will trick Godel. I mean, I'm smarter than Godel. What will I do? I mean, if Godel comes and says, you know, there is a statement, here is a statement that you cannot prove, and you cannot prove that it's not true in your axioms. So I'll take this set. So I have my set of axioms, and I cannot prove phi, and I cannot prove not phi. for some phi. So I'll say, okay, don't worry, I'll take the axioms and add phi as an axiom. Now I can prove phi. Right? Problem solved. But the Godel theorem tells me, oh, now there'll be another one that you cannot prove and cannot refute for every system.
Can we just keep adding all these phis into the axiom set? So we have a set that complex enough that
But then you'll use verifiability. Because you need a way to check whether something is an axiom or not. Right? Then you'll run into verifiability. So Godel proved this in 1930, and Godel's proof made people kind of feel uneasy. Because it looks like cheating. It was the kind of saying, someone who's saying, I am lying now. So, did I tell you the truth or not? If yes, then no. If no, then yes. End of story. You cannot prove it. That's basic. Anyway, so there was a lot of uneasiness about this proof. The proof looked very complex. You even have a book which is called Godel Escher Bach. Did I mention it already? I don't remember how the S before the C or the C before the S. SC, okay. Bach. Right. So Godel is the guy we are talking about now. Escher is this the guy that have those drawings in which you see one hand drawing the other. So you have two hands, each of them drawing the other one, and all kind of paradoxical drawings. And Bach is the composer. And there is this book by Douglas Hofstadter that talks about this, and it kind of says that the principle of Godel's theorem is the same as the principle of Escher's drawings and Bach's compositions, and it's a 1,000-page proof of Godel's theorem. So when I was a teenager, this was the way to show that you're smart. You have this book on your shelf. So I promise to prove it today, but just as to keep you coming to the next lecture, I'll prove it next lecture. But I'll prove it in less than 10 minutes. A complete proof of Godel theorem, and we'll talk about it some more next time. Okay, thank you.